moles per liter. We don't have to do equivalents per liter, so let's move on. Okay, so let's not worry about equivalents per liter. We can do that, but we don't have to. Next, we move on to concentration. Now we go into all the theory. Concentration depends on solution properties. There will be 4 properties that depend on the concentration of the solution. Exactly. You know that's technology, right? You have to class. So I think it's going to teach on Monday. I didn't even know that. Yeah, it says employee development day. It's a holiday. So you could make it we're going to finish this chapter which means when I think on Monday, I'm going to briefly go over the 3 chapters and start class. Okay, common properties are properties that depend on the concentration, but not on the identity of the substance. It doesn't matter what you have. It depends how. So let's talk about vapor pressure. Do you remember what I defined vapor pressure as? Vapor pressure is defined as the pressure exerted by the vapor over the surface of the liquid. Right? So there are all these molecules of vapor and they apply the pressure on the surface of the liquid. We're going to call that vapor pressure. And do you remember me talking about boiling point? When do you say a liquid is boiling? When do we say a liquid is boiling? When this vapor pressure is equal to the atmospheric pressure. Yes. Is equal to the atmospheric pressure, you say a liquid is boiling. Now, if it's a pure liquid, let me imagine this situation. So let's say you have a beaker and you have a liquid, right? Just some solution. Or even you have just pure water. Remember, it's only the particles that are at the surface that can escape. Because the particles inside, the water molecule inside, is actually trapped on all sides. It's connected to the other water molecule. So for a water molecule to actually become vapor, it needs to go to the surface. Now, imagine that you have something dissolved. It may take only a short distance to get to the surface. What vapor is escape, okay? I mean, whether it has to be one of the inside water molecules. It could be the water molecules that are right sitting on the surface, correct? But what if now I have a beaker, I have water, and I add salt particles inside? Kind of what you do when you cook. Let's say those big pebbles are drawn or your salt. Yeah? Now the water particles, especially the ones at the top, can escape, right? The ones at the top. But if you have to have one of these water molecules inside to escape, it needs to traverse a certain distance. It needs to travel a little more because it has to cross these pebbles. So it's going to take water molecules longer to become a vapor when you have something dissolved. So when you cook stuff, you're cooking something, the instruction always says add salt. Do you know why a little bit of salt when you cook something? Because it's going to take the water back to the boil. Because you cook your stuff for a long time. You're treating the molecules and you're taking them both to the vapor phase so slowly. If you take longer to become vapor, it's going to take as long as you reach the atmospheric pressure. So the water is going to put it more slowly. When you let it water, then it is just fuel. So that is a colloidal property. Okay, that is a colloidal property. Because it's going to be slowly more related to the anything that has what happens when you have very fine, you have any sort of salt, the phenomenon is the same. So it doesn't depend on what you have. It depends on how much. The more concentrated, if it's a very, very thin solution, really concentrated, what does it take for average and water? And the people do the worst. But it's tiny. Most salty water tastes good. The answer is yes. Salty water will give a lot to you. This is the next question you ask. You They put salt, keep that in the freezer, keep the water in the freezer, and we'll take a little bit of salt and give it a duration of 40 minutes. Go back and see what takes the pure water again and what takes the salt water. Yes? And you will see that the pure water tends to freeze a little faster than salt water. Why? Because I have a parting of the even during the water molecules coming closer. The water happens to freeze. They actually tell you. You get it? The sound is equivalent of what you have. Yes? So you can lower the vapor pressure. Right? So these pebbles in red are the equivalent of your salt. So you can now, if this is pure water, this is salt water. You can lower the vapor pressure. You can penetrate water molecules that much longer to escape. Yes? That is what to escape from here. Does that make sense, people? So, somebody molecules serve as a barrier to the escape of the solid molecules. Freezing point discussion. This is where I say that salt water you can even lower the temperature than the usual freezing point of water. This is a perfect example of why they sold the road in the winter in the Northeast. This is the Northeast. I think I the Northeast. You go to the East, and it's not the Northeast. You guys live in the Northeast? Why is it more of the Northeast? It's going to go there. And especially very, very harsh winters did not. You won't see good ice. The roof will not be iced out because salt water will prevent the water from freezing at the normal freezing temperature of the water. So the temperature is at 2 degrees. The will not be approaching. Or no. Why would that? And it was paid right? Which is a safer condition to blend. You could also boiling point elevation, so you can also elevate the boiling point by the same token by adding something to the solution, because now what do the particles do? They make it harder for the vapors to collect, which means the boiling point will take longer to reach. Okay? So both of these have to be understood. Freezing point and boiling point elevation. Does that make sense to all of you? So they're all very logical. We're not actually reading that in this semester. Okay? And the boiling point elevation, same thing, you just have to know the definition, you have to understand it, but you're not doing a math problem on it. We're not doing molality, we've already done molality, we're not doing molality. On that, please forget about that. The last one we're going to cover is osmotic pressure, and we do have math on this. So we're going to actually calculate the osmotic pressure. What is the meaning of an osmotic pressure? It's an actual phenomenon. Osmotic pressure is when you have a semi-permeable membrane, right? And you have water solution, and let's say, okay, so let's say you have a beaker, and you have pure water in it, pure water. And you put a semi-permeable membrane. So I'm going to say semi-permeable, SP, yes? Now let's say, the semi-permeable membrane is kind of goes right through the water beaker. But now let's say I add sugar or something to this side. So I add sugar. Do you know what the water on the other side will sense? It will now sense the concentration gradient. Now you have a concentration gradient. What that means is that the water molecule on this side, right? So I'm going to say this is left and this is right, okay? This is right and that is left. The water molecules on the right are going to sense the molecules on the left have more concentration, correct? So the water molecules on the right will start to rush in like this. You can see that? It will start to rush in, and the level of the water will start to rise on the left. the level of the water is going to rise on the left. If you want to stop this rise, what do you have to do? You have to apply pressure on this side, on the left. You apply a steady pressure on the left to keep the water level equal on both sides. And this phenomenon, the amount of pressure you have to apply, is called osmotic pressure. Okay? It's called osmotic pressure. Did you all get that, please? Okay. So the pressure you apply on this side is called osmotic pressure. Any questions? So what is osmosis? Can you repeat everything I said? Anybody? Alexis, can you do it? The osmotic pressure. What is osmotic pressure? Level, because when you add it, when you have a concentration gradient, you're going to have solution. It's only concentration on one side, but you're not going to have the concentration on the other side, right? Because you now have a semi-permeable membrane in the middle. So the water molecules, now remember, sugar is too big, so it cannot move. So when you add it to one side, it's going to stay on that side, but the water molecules are small enough to move. So they're going to rush to the other side because they want to dilute it. This happens inside your body every day, right? Right, that is it. And the cells, remember why your cells burst? You can have red blood cells that just break because if the concentration outside is more than the concentration inside your cell, what's going to happen? Actually, opposite. When the concentration inside your cell is more than the concentration outside, what is the water on the outside going to do? It's going to rush in. It rushes into your cell and breaks it. It's called lysis. Lysis means the cell breaks. Yes. Whereas what happens if the concentration on the outside is more than inside your cell? What happens? The water from your cell rushes out. And what happens to the cell? It shrinks. Or it dies. It's called necrosis. It happens inside your body. So this isn't something, so this is biochemistry.
Is that what happens with like dehydration?
Exactly.
What happens if you get to the people and the people that are shrivel up, like they have these it looks like the skin is moving down. Why? That's what I call osmotic pressure. That's the word. This is where it gets really confusing.
You see the formula? I here is the pressure. It's the osmotic pressure. Do you recognize the CG equals energy? This M is not molarity. That's the problem. You remember the big M? That's not the big M, people. That is osmolarity. It's this. Which you have to calculate, by the way. R is the coefficient of affinity, temperature, so all that's good. But the osmolarity is not the same thing as molarity. In fact, the osmolarity, I want you to write this down. The osmolarity is given as OSMOLARITY is equal to molarity times number of particles. It's molarity times number of particles. Okay? So you do need the M, the molarity M, to calculate the osmolarity. So let's look at an actual example.
So the R cells are one.
The gas. Very good. That's it. So look at this. Calculate the osmolarity. Okay, 5.0 10 to the negative 3. That is molar and what did I just tell you osmolarity is? I just gave it to you. Molarity times number of particles. Excellent. Now, I want you to tell me, do you see the molarity given to you?
5 times
10 to the negative 3. That is molarity. But I need number of particles, correct? So what you should be able to do is what we did in chapter 3. You should be able to say Na3CO4 will split up into how many particles? How many particles do you see in Na3CO4? In other words, how many ions do you see in Na3CO4? 4. Good. How did you come up with 4? Excellent. Okay, but I'm going to see that you come up with a plus. I know. I have to figure it out. Many people put it very little down there. Okay, minus. So then, how many sodium ions? In the Na3CO4, how many sodium ions are there? 1. No. Na3. Na3CO4. How many sodiums do you see? 3. So when I balance this equation, would I put a 3 in front of the sodium? Yes or no? Yes. And the PO4 is the whole thing. Remember, if it's parentheses on PO4, don't split it into PO4. The PO4, I see 1 here and 1 here, okay? Because I want you to know, how did they come up with 4 particles? Well, these are particles. That's 3 sodium ions and 1 phosphate is a total of 4. That's the formula of sodium phosphate, Na3PO4. That's the formula. Okay, so it's the sodium phosphate. Look up there. In that Na3, it's given to us. The formula Na3PO4 is actually given to us. All I did now is put it up. Because I need to find out how many particles it's going to get from that. Exactly, for a total of 4 particles. The PO4 cannot be broken down further to P and O. So, what do? I multiply this number by how many particles? And my osmolarity is now going to be this number. Did everybody get that? Okay, so new page. Calculate the osmolarity of. Okay, you want to go back and see it? Okay. Did all of us get this answer? Yes. Yes. Molarity times 4. Right? Yes, everyone? Molarity times 4.
Is there a particular way to write the hospital?
No. Yeah, it is osmolarity. Actually, moles of particles per liter or just osmo? Moles of particles per liter approximately. Yes?
So what is M used appropriate
For M, the big M?
for M?
Oh, a gas loss when we're solving. Chapter 5. Sure, why not? You can. Yeah, problems tend to do it in scientific notation. You don't have to. Yes? Okay, let's see if you can do another one. Calculate the osmolarity, okay, of a 0.120 solution of barium chloride. You're calculating the osmolarity, remember. 2.0 times 10 to the negative 3 molar. Okay, so I'd like you to find the osmolarity of these two solutions. A 0.120 molar, and 2.0 times 10 to the negative 3 molar calcium sulfate. Okay? Can you all try that, please? What happened? Think about the 0.120 molar barium chloride, right? How many particles did you guys say you get from A? Yes, because if you try to break it down, right, or what we call dissociation, yes, barium and how many Cls will you get? Yes. So total of how many particles? Yes, very good. So now our polarity is given by this funny looking M. It's written italicized. Is equal to, the molarity was what? What was the molarity in the problem? Point what? Times 3. Is that what you all did? Yes? Okay. And you get 0.360. It's just easy enough to do. But it's only easy if you know your ionic compounds and know how to break them down. If you don't know how to break them down, you're not going to know. Yes, yes. I will give you the polyatomics, but notice on barium chloride you didn't need the polyatomics. You needed to know the charge. Yes? What about the next one? Calcium sulfate. Well, let's see. What is the charge on the sulfate? -2, yes. So you get a calcium and you get a sulfate. Is that what you all got? So that's the total of how many particles? 2. Is everybody with me, please? So, yes? Okay, so our molarity will be equal to 2 times 0 times 10 to the negative 3 times 2. Yes, everyone? Very good. So what is it?
4.0 times 10 to the
Any questions? Okay, very good. So that is calculus. Now we're gonna. I'm gonna stop here first. When I see you on Monday, there's very little left. Okay, I'm gonna do the calculating osmotic pressure stuff, and then we're done. Okay, and then I'll start stuff. All right, folks. Thank you so much. We're gonna stop recording now. Times 10 to the negative 3 molar solution of potassium, of H2SO4. It's 2.0. Actually, that's how many steps. So sorry. KNO3. Change that to KNO3. Of KNO3. Well, we will get when we dissociate, say, what do you know dissociate? Yes, exactly. KNO3 can break down into how many particles is what I need you to tell me. Yes, because this is a polyatomic ion, isn't it? So tell me how many particles you can get from that? No. No. Okay, plus. Last entry. That is chapter 3. How many particles is that? 2. Number 5. Yes? You're going to take this number, 2.2, times 10 to the negative 3, and you're going to multiply that by the number of particles, which is what? Do it, and tell me what you get. You're going to go 2.2.
So how many particles do you get?
How many particles did we just get?
1 and 1.
Down
Plus
to 2
the
more.
charges, balance out there. So it's just 1 and 1.
6. Yeah, 1. Okay, so you're going to end up with 2 moles of particles. Right, everyone, or no? And you should therefore get, don't forget your liters stand for moles per liter, don't forget that. Yes? So you're going to end up with multiplying your molarity by the number of particles. Do we get that?
2 more particles. Right?
Yes, but no, what's the final answer? Yeah. Please agree with Emmanuel? So you get 4.4, but I'm assuming the other units. What did you say? What are the units? Osmol. Very good. People, you cannot afford to forget. Did you? Oh, yes.